Up till now, we've been working almost entirely in simulation to train an AI agent that balances a bot like this one. We have a preliminary agent that we can now try deploying to the real robot. As you'll see, there are differences between the simulated world and the real world, and the agent never learned to deal with those differences. This is known as the sim-to-real gap, and we'll talk about how to deal with them in this episode and in the next episode. But with that, let's get started. In the previous episode, we trained an initial agent using PPO. This time, we're going to deploy the agent to the real robot and discuss the sim-to-real issues. If you recall, our AI agent consists of two different neural networks, an actor that takes in an observation to produce actions, and a critic that takes in the same observation to predict the total future rewards from the current state. During training, we updated both of these networks, as the actor relied on the critic's predictions to know if it was making good decisions. However, once training is done, we don't need the critic anymore. We can just deploy the actor network to the microcontroller on the robot. So now the robot just needs to create an observation using its various sensors, send that to the actor to perform inference, and use the results to drive the motors. With that strategy in mind, let's make it happen. If we go back into our PPO file here, if you remember, we have this export actor ONNX function that we looked at in the previous episode. All we're going to do is pass in a path. We're going to pick the best model that performed during training. We're going to pass it into here, and it saves out that ONNX file, which we saw previously. With that, we have this ONNX2C. Now, I called it actor here, but the reality is you could probably put any dense neural network in here, but it assumes you have hyperbolic tangent activation functions along with fully connected layers. So it makes a lot of assumptions, and it works pretty much just for our reinforcement learning project. You have a number of different ways to convert a model to microcontroller code. There are some runtime environments like LiteRT for microcontrollers. This was formerly known as TensorFlow Lite Micro. You might have an NPU, an AI accelerator on your chip, in which case you probably need to use the vendor's proprietary methods to convert it. You also have RAW-C, which is what we're going to do here. There's no acceleration for this, but rather than trying to stand up TensorFlow Lite for micros, we're just doing a basic multiply and accumulates with a tanh activation function. Turns out that's pretty simple to do in C code, and the actors are generally small enough we can run them in 2 to 3 milliseconds just through the very fast CPU that's on the ESP32. This works just fine. So once again, I asked Claude for some help for this, where it reads in an ONNX file, and then it converts it to raw C code. So it just reads it in, reads the layers, and then spits out the multiply and accumulates for the different nodes, and then the tanh activation using math.h to perform that. That's really it. We're just going to call this script to convert our ONNX file to raw C code. It's going to drop it out as a .h file, which we are going to include in our microcontroller code. I'm going to use Arduino because I find it to be fairly simple and easy to use for this example. If you bring up your Docker container, let's open up a terminal. We're going to go into Workspace Software. This is what we've been working in. We're going to run the script that's in the RL directory, but you'll need to find where that ONNX file is located. So using a browser like this on the host computer, I'm going to go into the previous episode. Let's go into runs, and you'll see the two phases we have here. I'm going to sort by date so we can see the last run. If you go into the first run, you just see the information from that run. And then the second run, we actually have our ONNX file and then the associated ONNX.data file. These usually come together. So this is the folder that we need. I'm going to copy this folder name because we're going to need that here. We're going to run our ONNX actor to C as a Python script. We're going to look in the O2 balance bot with PPO. That was the previous episode folder. We're going to go into runs. I'm going to paste in that directory name, and there should be an actor.onnx in there. So that's the input. Then we push space. I'm going to go into the same directory, paste in that directory name, and I'm just going to call it actor.h. It's going to drop it right in there. So we're going to run that script. It should print out the weights that were found, give you some information about the layers, the observation, the actions, And then if we bring up the directory again, sure enough, there is actor.h. Feel free to open that in something like VS Code, and you can see the C code that was spit out. It was automatically generated, and you see our first layer with the 16 nodes. We've got the weights, the biases, and so on. This is the forward pass. You can see it doing the multiply and accumulates. It does the hyperbolic tangent activation functions for both of those layers, and then it gives us 2 outputs for that final layer. It's pretty simple to do a forward pass for a dense neural network like this. This is all we need, and we're going to copy this into our Arduino code. For this next part, you'll need the physical robot. If you have not already done so, unbox your M5Stack BALA 2 Fire and attach the wheels. Connect a USB-C cable from your computer to the robot and put it on its front or back face. If you go back out to the software directory, let's go into our O3, this is this episode, Sim to Real, we want the IMU calibration code. If you open that up, which I've got open right here, you can see this calibration code that I took from the M5Stack's original calibration code, stripped out the unnecessary stuff and just focused on calibrating the gyroscope and accelerometer. While the BALA 2 should have its IMU factory calibrated, it's often a good idea to make sure it's calibrated for your intended environment. So I do recommend running this once just to calibrate your IMU. It's going to call the built-in calibration functions that come with the M5Stack library. So if we go through here, you can see where it tries to load it from non-volatile storage first. It gives you a warning if it finds something already there. You'll probably find one from the factory already there. We set calibration, so we're just calling these M5Stack functions, and this is just what's in their calibration code, where it runs the gyroscope calibration for a few seconds, telling you to place the robot on a flat surface and don't move it, so it figures out what not moving looks like for the gyroscope. Then we disable gyroscope calibration. We do a similar thing for the accelerometer, but the accelerometer requires you to move it around to each of the faces, so it will tell you that as it goes through each of these steps. You're welcome to use any firmware environment you'd like to program this. You can even use ESP-IDF. I like Arduino because M5Stack has a pretty solid library for it, and we can use libraries for things like the ESP32, for things like Wi-Fi, and it works pretty simply out of the box. That way we're not spending a bunch of time messing around with the firmware, where the example and demos for this just work with Arduino. So it's a nice environment for this, but if you don't want to use Arduino, you're welcome to use something else, but I will be using this for now. So to get the Arduino library, I'm going to go to File, Preferences. I'm going to go to the Additional Boards Manager URLs. Let's click that button. Scroll down to the bottom here, and you will need to paste in this URL, this static cdn.m5stack.com/resource/arduino/package_m5stack_index.json. So with that, click OK out of those. Let's go to Boards, search for M5Stack, and then you will want to install this M5Stack official library. I've already installed it, but you should have an install button here. Click that and wait for that to install all of the libraries and drivers for the M5Stack boards. That should have everything you need. So go ahead and make sure that your BALA 2 Fire shows up here. If you don't see it, select Other Board. I search for Fire. Down here, you should find the M5Stack version of the BALA 2 Fire, or actually it's the M5Stack Fire that's the main board. The BALA 2 is just a set of libraries from the software perspective. So we need the M5 Fire. Looks like there is an ESP32 version. So if you installed the ESP32 boards, you might see this as well, but I'm going to go with the official M5Stack version. So make sure that's selected. Plug in your board or your robot, select the COM port, click OK, make sure that's selected, click Upload, and wait for that to compile and upload to your board. Open a serial terminal and follow all of the instructions. Place the robot on a flat surface and press Enter. It will take some readings and use it to calibrate the gyroscope first. Then you'll rotate the robot to have the named face be down and leave it for a second before rotating it to a new face. When that's done, it should save the calibration data to non-volatile storage on the ESP32. Now we can go to Open. Let's go into our workspace. Software, episode 3, we're going to start with BalanceBot. We've created a couple of local libraries. The first is this BALA.h. This is a version of the modified BALA library from the M5Stack folks. The only thing I did here was use the raw I2C reads and writes rather than theirs. That just makes this library a little more portable. And I found that the I2C worked a little better, at least from my experience, but it should work either way. I've included that here. I just copied and pasted it here and just changed out their version of I2C with wire.h. So this should all work the same. This is used to communicate to the STM32 microcontroller on the bottom side of the chassis. There's another PCB on there with the microcontroller that actually controls the motors, and we talk to that using I2C commands. And this just gives us an interface to talk to that other microcontroller. The other thing is this actor.h. This is that auto-generated actor that we created from the ONNX file. We just pasted that file right in here, and there's a couple of functions we can call. In the actual sketch, we're going to set up some options here. We're going to be using that complementary filter that allows us to mix the accelerometer and gyroscope information to create pitch rate. This is a common way to do sensor fusion, really basic sensor fusion. We have our step time. This should be 5 milliseconds. This should line up with what we were training with. We have our motor scale. I'm doing this in float because that's what the library expects. But remember that our neural network, the actor, gives us an output that's normalized motor control from -1 to 1. So we want to just scale that from that normalized value to something between -1023 and +1023. We've also looked up the number of encoder ticks per wheel revolution in order to get the wheel or the motor speed. We have a tip threshold. So if the robot tips more than about 45 degrees, we just stop the motors. That prevents it from running off if it's fully tipped, and we can stop execution just by turning the robot over. We also have the motor directions. Note that the motors in the simulation might be opposite control of what it is in real life. So all we do is just have something here that allows us to multiply by -1 if we just need to flip the motor direction. We also have the encoder direction that's similar. We might be reading in the wrong direction. So after some testing, I found that, yes, the encoders read in the correct direction, but the motors are not controlled in the right direction. So we just multiply any controls by -1. And then we've got a reset period. So if you flip the robot over and then flip it back upright, it waits for 1 second before running again. We also get encoder ticks to radians. That's going to be useful for our radians per second calculations. We set up some globals here. The BALA global, I believe, should come from this BALA class. Yeah, here we go. So that's what we're importing here, and we're going to use that class to control the robot. We then configure the library that we've imported. That's the M5 Unified library. Speaking of which, if you have not imported that, you'll need to go to Libraries, search for M5 Unified, and install this library. That gives us access to the M5Stack functions and classes. So we set up that. That allows us to do things like talk to the IMU that's on the actual M5Stack board. We initialize our serial. We're going to load that calibration data that we just saved to non-volatile storage. We do that with this load offset from NVS. We then clear out our encoders because we're starting from scratch here, and we make sure the motors are not spinning. Then we wait for 1 second to start. Inside the loop, we get a timestamp. We read from the IMU. So we do this by calling this update that actually updates the values in the IMU, and then we read them, usually from the library. So this should fetch the information from the IMU that's saved in the library, and then we fetch that information from the library. So we're just getting these fields here. And from that, we just need the IMU data, and we get the Y and Z axes from the accelerometer. We then use the gyroscope information to calculate this pitch rate, and we calculate the pitch rather than the pitch rate, which I said earlier. We calculate the pitch with that complementary filter using a combination of the pitch rate, and the pitch as calculated from the accelerometer, which is using a little bit of trigonometry. We then read the encoders. This is just the BALA library, get encoders. That reads it from the connected STM32 microcontroller on the robot side. We multiplied that by our direction encoder, so 1 for each, in case those were backwards, but they're not, should be fine. We then compute the wheel velocities. We should get this in radians per second. We check to see if it's tipped, so we store that, and if so, we basically just skip it. We don't run inference, and we just stop the motors. So if the robot's not tipped, the first thing we're going to do is construct our observation vector, which consists of the pitch that we calculated using that complementary filter, the pitch rate, which comes from this gyroscope information. We get the left and right wheel velocities that we got from the encoders. So that becomes our 4 elements in this observation vector. We then run inference. So we are going to create an action that's going to be 2 actions. That should be 2. Yep. We are going to pass in the observation vector, and we're going to pass in a reference to this action array that gets filled out in this actor forward. Actor forward comes from this actor.h, and this should be a very basic function right here, where we just pass in these 2 pointers, and once inference is done, it writes out to this output, or in our case, the action array that we set up here. We then clamp our actions because the inference might give us something outside of -1 to 1, but we are only really trained to deal with -1 to 1, that normalized action vector. From there, we calculate the actual motor velocities by multiplying the action element by the scale. So we convert that -1 to 1 to something between -1023 and +1023. We then set the motor speed. So this is that BALA library here. Set speed, all that's going to do, if we find it here, set speed, that just writes out to the other microcontroller that actually controls the motor drivers. And that's it. It's pretty straightforward. Now that we have our neural network, the actor, that's been trained and deployed as pure C code right here. Feel free to go ahead and start uploading because it's going to take a minute. But while we look at the rest of this, if the robot has tipped, we are going to set the speed to 0, and we're just going to basically sit here waiting for the robot to be uprighted or set upright, and it waits a second before starting it over again. We also want to take a look at the amount of time left. Reading from sensors, performing inference, and writing out to the motors should take about 2 to 3 milliseconds, which is well under our 5 millisecond interval time. So we just wait to fill up the rest of that time. You're welcome to do other stuff there, but this is fine for what we're doing on this particular core. This is just a section to print diagnostics that was helping me to debug. I've set debug to 0, so this should not get printed. I did find when I turned this on, it started taking longer than 5 milliseconds. This would be printed every 20 iterations, but it would still take longer than those 5 milliseconds for that iteration, throwing things off. And it looks like I forgot to indent there. Good enough. And that's it for our code. With everything uploaded, we can see how it runs. The robot balances briefly or with some help. However, it eventually drives off and tips over. Even though the robot was balancing great in simulation, it struggles in the real world. This is the sim-to-real gap that we discussed in the beginning of the episode. It could be due to noisy or miscalibrated sensors, inaccurate motor torques, noisy environments, the robot not being modeled exactly correctly, and so on. There are a number of ways to address this. I know that some robot shops, like Disney Research, spends a lot of time modeling the robot exactly as it appears in the real world and ensuring the physics of the sensors and actuators are accurate in simulation. Another common way to handle this gap is to use domain randomization, which we'll explore in the next episode. Finally, we can try to add some filters and offsets in our firmware to make up for the inaccurate agent. Let's see how that works in practice for our balance bot. I've already created these fixes for us, so let's go to Open. Let's go to our repository that we've been working in. In Workspace, Software, 03, we've got Balance Bot Fixes. So this is where I've put all of those fixes. You'll notice that there are more settings now. So we've got a pitch offset. We want to tune this so the robot stays upright. This essentially just gets tacked on or added to the measured pitch. If you see your robot pitching forward or backward and wanting to lean a certain way, just adjust this value so that the robot stays upright. I noticed that the motors had a lot more power when connected to USB because I'm assuming the motors were getting, say, full 5 volts from the USB, but when I ran it on battery, the motors seemed to drag a little bit, which makes me believe that the battery didn't supply enough power or enough voltage to the motors, and we can just boost the output we are getting from inference by some amount. I found that 1.5 worked decently well. We can also add an action deadband to prevent the motors from making small corrections and jittering back and forth to try to balance. I also added a low-pass filter. This is an infinite impulse response, or IIR filter, that simply use the actions from the previous iteration and mix them into the current actions to create this simple low-pass smoothing filter. However, do note that it adds more lag in, but it does seem to help with balance and some of the jittery motion. The rest of this should be the same. So we've got the complementary filter, the time step, motor scale, all of these should be the same as before. So let's scroll down to see what we've changed. We load the calibration data, we set up the motors, zero out the encoders, all of that is the same as before. So we read from the IMU, we use that complementary filter to create this pitch. We read the encoders, compute the wheel velocity, see if it's tipped, and then this is where we start adding in our own stuff. So after we run inference here with that observation vector, we get the action result, we constrain it, and this is where we use that low pass filter to smooth out the motor commands. So you see we have our action alpha here, which you can tune. That determines what percentage of the previous action, this action filter, gets mixed in, and then we add it to the other percentage. So if this is 90%, it's 10% of the new action. So that just creates this low pass filter for both left and right wheels. We can also apply this deadband. So if the absolute value of the action is less than, say, 0.02 in this case, basically don't move the motors at all. This creates a deadband, so hopefully it just settles on some position in the wheels. We can also add a boost. So we have the actual values we are sending to the motors. So we've got the direction. In this case, it's just -1 because the motors are actually attached backwards than what we predicted in simulator. That's easy to correct. We've got the action as we computed from the action up here from the filtered information and applying the deadband. We apply the scale to convert to something between -1023 and 1023, and we multiply by the motor boost. I found that to run it on battery, we needed to boost the action to the motors by 50% in order to get it to work and balance appropriately. So a lot of that's just tuning these variables to get the bot to balance somewhat smoothly. If the robot is detected as tipped, basically just turn off the motors, reset everything, and wait for it to be set up right again. Everything else is the same, so we can go ahead and upload this to the robot. As you can see, the changes we made to the firmware help the robot balance much better. However, it means you're spending a lot of time tweaking filters and coefficients to get it to work in the real world. This kind of defeats the point of having a robust agent learn to deal with these kinds of offsets and inaccuracies. You might as well just create some PID loops to tackle the balancing problem. However, we're going to discuss domain randomization in the next episode. We'll roll these inaccuracies into noisy readings or motor control in the environment. The agent will have to learn to deal with that kind of noise. While it means more training and probably a bigger neural network, the agent will be more robust and hopefully not require nearly as much post-processing in the firmware. Come back for the next episode if you want to see how all of that works. See you then.